This is section 3.9, part C. We're going to return to the problem of solving an equation that contains a logarithm, or in this case, more than one logarithm. And what we're going to find out is that it is the collected form that's more valuable to us when we're solving log equations. So our strategy is going to be to start by getting all of our logs on one side so that we can write then the collected form. After we've got the collected form, we should be able to use the exact same strategies as we used in section 3.8 to solve the problems. So as I look at number 1, I'll begin by saying, let's go ahead and take those multipliers again, put them back up as exponents to work toward a collected form. So I'd have the log base 4 of x to the 9th. Subtract the log base 4 of x cubed to the 2nd power equals 2. Let's take care of that x cubed to the 2nd power. Power to a power, I need to multiply those exponents, so that's really x to the 6th. All right. My logs are subtracted, so I know I can use that quotient property to bring them back together as a single log. We'll make that x to the 9th over x to the 6th. And let's see, dividing, I subtract exponents, so that would be x cubed. All right, now that I've got my collected form, I want to get rid of my log base 4, and I know the inverse of the log base 4 is the exponential function base 4. So I'm going to use 4 as the base, and raise it to the log base 4 of x cubed power. And I'll do the same thing on the other side. Use 4 as the base, and raise that to the 2nd power. I have my inverse functions that get rid of one another. Do and undo. And so the left-hand side just becomes x cubed. And the right-hand side, 4 squared, would be 16. I could take the cubed root, or the 1/3 power of both sides. The exact answer is 16 to the 1/3 power, or the cubed root of 16. The approximate answer is about 2.52. All right, let's try a couple more of those. In number 2, once again, I see I have 2 logs. They are on the same side of the equation, so I'm in good shape there. And since there are no multipliers, I can start right out by saying, all right, great, these are added. Let's collect them into one log by multiplying the arguments. The log base 5 of x multiplied by x plus 4 equals 1. I'll go ahead and multiply out inside the brackets. Make that x squared plus 4x. And now that I've collected, so there's just one logarithm, again, go back to what we learned in the last section. I want to get rid of a log base 5. The inverse is an exponential with a base of 5. So base 5, and I put everything on the left-hand side in the exponent, and the same thing on the right. Base 5 raised to the 1st power. Exponential base 5 and log base 5 are inverse functions. So all I have left is x squared plus 4x equals 5. This time I ended up with a quadratic, and I'm thinking I probably want to get that equal to 0. That's our typical method for solving quadratics. So let's subtract the 5. And I would be looking for a sum of 4, product of negative 5. 5 and negative 1 should do that. So x plus 5, x minus 1 equals 0. Giving me x plus 5 equals 0, or x minus 1 equals 0. X equals negative 5, or x equals 1. All right, we have to be careful here. We got a negative solution, and we probably should check and make sure that's not going to cause problems in the original equation. Remember, you can't take the logarithm of a negative number, right? The domain of the logarithm function is positive numbers only. Clearly, if I tried to plug that negative 5 in here, I'd be in trouble. There is no such thing as the log base 5 of negative 5, at least not with real numbers. So I'm going to throw this one out. Not in domain. The 1, however, is no problem. So I'll keep that x equals 1 as my only legitimate solution. All right, third example. Here our two logarithms are on opposite sides of the equation, so I do need to get them together on the same side, otherwise it will be impossible to collect them. So let's do that. I will add the 3 log x to the 4th to bring it over to the left-hand side. All right, we do have multipliers again. So I've got to put those back up as exponents as part of my collecting process. So I'd have the log of 2x to the 2nd power plus, the log of x to the 4th to the 3rd power equals 4. Let's go ahead and just simplify those. 2x squared would be 2 squared is 4 times x squared. And power to a power, I'm going to multiply those exponents. X to the 12th. Now that they're individually simplified, I can collect them. These are added, so that's going to take me back to the product property. I'll collect as a single logarithm of 4x squared multiplied by x to the 12th. Adding powers, that would give me 4x to the 14th. All right, the logs are all collected. And so now to solve the equation, I need to get rid of the logs. This is a log base 10, so its inverse would be an exponential base 10. So there we go, base 10 raised to the power, log of 4x to the 14th. And same thing on the other side. Base of 10 raised to the power of 4. I have my inverse functions, doing and undoing. So what I'm left with on the left-hand side is 4x to the 14th. And on the right-hand side, 10 to the 4th, or 10,000. All right, we're getting there. Let's divide both sides by 4. That's going to give me x to the 14th equals 2,500. And I want to get rid of that exponent of 14. So I'll raise both sides to the 1/14th power. Multiplying just gives me x to the first. And 2,500 to the 1/14th, or the 14th root of 2,500, is my exact answer. I can use the calculator to get a decimal approximation for that. It's about 1.749. Oops, sorry. Glare there. All right, we've got one more. Oh, and by the way, these are positive values. Looking back, plugging in positive x values, no problem. We are just fine as far as being in the domain. Technically speaking, since that was an even root, I probably should have considered the negative 14th root as well, but that would have caused a negative inside the log, so it's just as well that I didn't. All right, our last example. Once again, the logs are on opposite sides, so I'm going to go ahead and add the log base 2 of x plus 8 to bring it over to the left-hand side. There are no multipliers, so I don't have to worry about bringing anything up as an exponent. I can just go right ahead and say these are added. So I'm going to go back to my product property again. The log base 2 of the product, x plus 7 times x plus 8, equals 1. I'm going to multiply out what's inside the brackets. I will get x squared, a 7x plus an 8x for the inners and outers would be a plus 15x plus 56. All right, my logs are all collected, and I need to get rid of that log base 2. The inverse function is an exponential base 2. Same thing on the right-hand side, right? Exponentiate on a base of 2, so that becomes 2 to the first. I always have to do the same thing on both sides. And there are those inverses again. So I have x squared plus 15x plus 56 equals 2 to the first, or just 2. I'm back to a quadratic, so I'm going to go ahead and get 0. Let's subtract that 2. And now let's see if that one factors. I would need a sum of 15 and a product of 54. I believe 6 and 9 will do that. So x plus 6 times x plus 9 equals 0. If x plus 6 is 0, that would give me x equals negative 6. And if x plus 9 equals 0, I'm going to get x equals negative 9. Now, they're both negative answers, but that doesn't necessarily mean that I have to throw them both away. I need to check to see if they're in the domain. If you look back to the original, if you plugged negative 6 in for x, that would be the log of 1. That's okay. And again, over here, if you plugged negative 6 in for x, you'd have the log of 2. That's also okay. So negative 6 is in the domain. Let's check the negative 9. If I plug negative 9 in for x, now I'm taking the log of negative 2. And I cannot take the log of a negative number. So this one's not in the domain. All right, that brings us to the end of Part C.